So I made my own video for this problem, actually an old FRQ, and it's kind of a funny story behind it. It was actually part of one of the videos that they made for they were putting on YouTube for those AP reviews. But the teacher that was teaching it, she was doing it live, and she kind of got crossed up a little bit and did a really common mistake, and then kind of had to backtrack. It really took a while, and I thought, oh, I'm not sure I want to use that as a good snippet for you to watch. So we actually had a real good exchange over email. I said, hey, I got the idea she wasn't sure where she got crossed up, but she did recover okay. And we had this great conversation back and forth, and we, figured it out and discussed it and whatever. So I thought, you know what, I'll just make my own, because this problem, if ever there was a perfect problem for seeing all the different areas in rotation, this is it. Like, it covers some kinematics, it covers moment of inertia, torque, energy, Newton's laws, like almost everything except for angular momentum. And if I wanted to, I could probably get that in there, but I want to keep this manageable. I don't know, this might go a while, but there's so much compacted into this. If you can kind of tune in and get all these little details, you might catch some things and see these connections that I know rotation's hard, but maybe some things will kind of synthesize here a little bit. It's actually a very simple arrangement, and there's so many things you can do with a problem like this. So so we got the picture in front of you. It's just a little hoop that's rolling down a ramp, and then it rolls onto a table, and at some point it's going to fly off the table. I'm not really interested in that so much right now. I'm just interested in the first two parts. So if this goes too long, I might cut that part off. But so it's released from rest. They give you the moment of inertia, which in my opinion, they shouldn't have to do that for a hoop. A hoop is the one shape that you can use the equation right off the green sheet for. mr squared describes a hoop, but that's only because all the mass is the same distance away from the center of rotation. If you have some of it like inside, like a disk or something, it makes for less. So Mr. Frensley, on his video, he called it the multiplier, I think, the shape multiplier. I think that's a really neat idea. Disks is a half, and like spheres are 2/5, and but for a hoop there is no multiplier. So anyway, it rolls down smoothly. That's a really important thing. It rolls without slipping. I'll tell you why that's important. And we don't need to worry about the height, because right now we're just going down this far. And here's the key. We're looking for an acceleration in part A. So I hope that when you see acceleration in a problem like this, your first thought is, oh, that's a Newton's second law thing, because Newton's second law has the F equals ma in it. Part B, just to show you what's coming up, we're finding a speed. Now, if you're asked for speed, I hope the first thought that's in your head is, that's part of an energy expression. Kinetic energy relates to speed. Now, it turns out you can do part A with energy, and you can do part B with Newton's laws, but it's kind of clunky. So if they're setting you up for Newton's laws, by golly, just go ahead and use it. So anytime you're using a Newton's second law approach, you should really start with free body diagrams. So we only have one object that's moving here. So I'm just going to draw it up here. I'm going to draw it kind of big. And when we first started doing free body diagrams, I said you can just draw a little dot to represent your object and draw the forces from the dot, put the tails all together. But that changed when we did rotation, because with rotation, we start talking about torques. And for torques, it depends on where that force is actually applied, where the contact happens. So I'm going to be careful to draw these things this way. So I am going to put a light little line here just to represent the ramp so we can see that point of contact. So we obviously always have the gravitational force, mg, called weight. Now I draw that dashed. And that's because when we have an inclined plane, we don't ever use that force by itself. We use the components that go down the plane and the component that is perpendicular to the plane. So I'm actually going to replace this with solid components. This one called mg sine theta. I'm not showing the trig, but my hope is that you've done enough of these that you remember that the one down the plane is sine of theta, and the one I say pushing into the plane is cosine theta. I mean, I could do a geometric proof of that, but that'd just be more time. So, so that's the weight force. And then we have a contact with the actual inclined plane. So that does two things. It makes the perpendicular force, we call the normal force, that starts right here. So this is going to get awkward because I'm going to draw it from this point, and it's going to go straight along where my component is, but the normal force just points like that. Okay? And the other part of that contact force is static friction. Now, here's an important thing to remember about rolling. I didn't make a part just about rolling, but this really pertains to it. When things roll smoothly, it is static, not sliding friction. Smooth rolling means the surfaces don't slide across each other. And so this was actually the part of her video that she messed up. She labeled it friction, but she didn't think about the fact that it's static friction. So those are all the forces because there's nothing else making contact. So we're going to build, and I remember doing this, you might remember this too. I had this big, long, elaborate thing. I'm not sure it went all as well as I was hoping it would, for building Newton's second law equations from these diagrams. And it kind of went like this. You look for any forces that are along your acceleration direction, and any force gets included in your equation. Okay, you just assemble them together. So for the acceleration down the plane, okay, again, I'm building this from the diagram. That's why you have to do the diagram first. So for this part, it doesn't matter. We're not doing torques. We're just doing forces. So ignore where the forces are applied. We've got an mg sine theta down the plane, and we've got a friction force up the plane. Those are opposite each other. I always put the one first that's in the direction of the motion, or the direction of the acceleration, which is both down the plane. So that's an mg sine theta. And then the one that's opposite that, this is how I take care of my directions. I just make it subtraction. And Miss Frenzold, Jensvold is her name, she suggested that as well. Sorry about the dogs. Mr. Frensley, I think, also suggested this. I can't remember exactly, but this was the error in the YouTube video. You cannot use mu Fn here because for static friction, very rarely is static friction equal to mu Fn. Okay, only when you're at the critical point of it's just about ready to slip, but that's not the case here. So those are the only forces we have. So we end with ma. Okay, so this is F net equals ma, just customized for this situation. Okay, now for the acceleration, this is you see how the ball would be spinning clockwise? For the clockwise rotation, we're also accelerating. Okay, but this time, because it's rotation, we're going to use the rotation version of Newton's second law, which I think I'm going to write it here because it's a little less familiar. It says the net torque equals I alpha, where alpha is the angular acceleration and I is the moment of inertia. So they gave us the moment of inertia here, which again, I don't think they had to. You have to recognize what a torque is. A torque is any force that's not applied or doesn't go through the center of rotation, the axis of rotation. So there's only one force of all the forces here that doesn't pass through the middle, and that's the friction force. So do you see, like, if I were to put a pin, like I'll put my pen cap here, I put a pin here, and I tug on this with a friction force, it tends to rotate it clockwise. I'll do it a little more slowly so it shows up. That's the torquing force, okay? Now, not every force is a torque, but every torque is caused by a force. Here's the other mistake people make. A torque is not just the force. It's the force multiplied by the distance that force is applied from the axis of rotation, and it's a cross product if needed. Now, if things are already 90 degrees, you don't need to worry about the fact that it's a cross product. So sometimes we say RF sine theta, but sine of 90 is just 1 anyway. So here we have, here's the little distance. The radius of the ball is that little r, that distance. And we have 90 degrees to it is the friction force. So we do not have to worry about that direction part. So I'm going to write it this way. The friction force times r, that's my torque, equals I. Now I was given here as mr squared. And for another shape, it would be a different multiplier in the front. And then what is alpha? Okay, here's another critical point. When you have rolling without slipping, then your acceleration down the plane has to kind of match the acceleration of the spin. You can't start it spinning too fast for it to keep up, because if it spins too fast, it's like spinning your tires on your car on icy roads. And if it starts to go down the plane too fast and the spin can't keep up, then it's actually sliding. So if we have smooth rolling, the relationship between the two, I'm going to write it over here, without slipping means that alpha is A divided by R. Or sometimes it's written A equals alpha times R. Okay, that is actually on the reference page, but it's in a rather cryptic form. They write this for velocities. The velocity of something that's not slipping. V equals omega R. But if we take the derivative of both sides with respect to time, you get the acceleration relationship. So I think this is like a free equation. But remember, on the AP exam this year, you can have this in front of you. So write these things down. You can have this problem in front of you as far as I'm concerned. So then A over R gets put in there. Okay. So this is actually a really nice relationship, and it ends up pretty simple. Because look what happens. The R's all go away, and the M's go away, and you end up with a pretty simple friction force is, oh, I said that wrong. M's don't go away. Is M times A. Okay, so R's go away. Friction force is M times A. So now I'm going to take this MA, and I'm going to replace the friction force here with that. So mg sine theta minus, now here's where my substitution happens, MA equals MA. Now be careful, don't do an algebra boo-boo here. These don't cancel out. You can actually add MA to both sides, and you get 2MA. Then the M's cancel, that's where the M's cancel. And you get, acceleration is 1/2 g sine theta, which is kind of a cool little relationship. Here's something that kind of relates to that, but not really. If there were no friction, and this were to just slide down without rolling, okay, it wouldn't have to tie up its motion into rotation so it could move more quickly. It would accelerate at just g sine theta. So it has half the acceleration it normally would because it has to rotate along with this, okay? So there's part A, I think a critical part, and again, I think worthy of taking 10 minutes to look through that. So now we'll look at part B next. Okay, so now we see we have nice uniform acceleration down the plane of 1/2 g sine theta. Now we're asked for how fast it's going to be going when it gets to the end. Notice they gave you the distance L, which I think is kind of nice. So you could just pretty easily do kinematics for this. When you have uniform acceleration, those first equations on the reference page are great, especially the one that says v squared is v naught squared plus 2a, and then I'll use delta x here. Well, we don't have v naught. I mean, we have it. It's 0. And so the velocity is just the square root of 2 times the acceleration, which is 1/2 g sine theta, times delta x is how far it's moved while it's accelerated, and that's L. And so we get a pretty simple relationship here of the square root of GL sine theta. So that's kind of nice and simple, right? But now let me show you an alternative that would be great if you hadn't already done part A. Let's say you didn't know what to do in part A. When you see part B, when you see speed down here, I want you to think energy. Conservation of energy is such a useful approach because it says this. It's like when we're perched here on the top of the ramp, we have only gravitational potential energy. Okay? MGH is the simple relationship when you're here near the surface of the Earth, MGH, where H is not this H here, but this distance here. Now, what is that? If you use geometry, there's the hypotenuse of this triangle is L. So this is L sine of theta is like the height on the ramp. Okay, so we could figure out an expression for its potential energy, and then it all turns into kinetic energy down here. Now, here's where rotation comes in. When things rotate, it's not just 1/2 mv squared, because that accounts for the v, the translational, the motion forward, but it doesn't account for the fact that there's a lot of energy in all those particles because they're spinning around the center. Okay, so even if something isn't moving forward, if it's just spinning, it has lots of kinetic energy, and that expression is 1/2 I omega squared. That's on your green reference page. So how do you account for both of them? Well, you just combine the two together. So all the gravitational potential energy we start with becomes both forms of kinetic energy combined, a 1/2 mv squared plus 1/2 I omega squared. And those two are linked together as well. You can't have any old amount of rotation kinetic energy plus translation. They have to be kind of coupled together if it's not slipping. So here's how that comes out. So on an exam, I would write first conservation of energy. That tells the grader what approach you're using. That's just a nice thing to do. And then they should recognize when you write mg L sine theta, You might write h, but golly, if you write h, it makes me nervous because that h is there, and I'm afraid they'll think you're using the height of the table. And then at the bottom of the ramp, here's where you're showing that you know about rotation. 1/2 mv squared. Okay, that again accounts for the downward motion of the hoop, even if it weren't spinning. Like if there were no friction, it would do that. Plus the fact that it's spinning means 1/2 I omega squared. Okay, now we're given I, and here's the other thing. Remember up here I talked about rolling without slipping, that important relationship. That also means that the velocities are coupled together. The v and the omega have to be tied together in the same way. V equals omega r. And I think it's equation 11. I'm going by memory. I don't have the reference page in front of me. In my class, we've numbered the equations. So let's just substitute those things in there. mg L sine theta equals 1/2 mv squared plus 1/2 now mr squared for I and v over r squared for omega squared. Now we can start canceling a bunch of stuff. See here we've got the m's go away and all these r's over here, the r squared and this r squared goes away. So we have 1/2 v squared plus 1/2 v squared here. So I'm just going to write one more step. G L sine theta equals half plus a half is 1 v squared. So square root both sides. We have the square root of GL sine theta, which of course agrees with our kinematics approach that we used before. Okay, so gosh, that was a lot of rotation stuff in there, and I love all of it. And if you had the patience to sit through 17 minutes of this, you saw, I mean, I can't think of very many more concepts we could fit in there. Okay, but let's look at the rest of this problem because there's some more stuff yet to see. Okay, so if you're not interested in looking at a projectile motion part, I give you permission to skip part C and just go right on to part D. Part D is some more rotation. But they want to know the horizontal distance from the edge of the table the thing would land. So, you know, once it rolls down the table, reach the level table, it's going to move at that same speed that we found here in part B, and then it becomes a projectile. So the thing to remember about projectiles is the distance they move this way, we'll call it x, depends on how fast it was moving at the moment it became a projectile. That's just the horizontal motion that we found earlier, but also how much time it has to move forward. Okay, so the fact that they gave us this height here is going to lead us to the time, just to map out my strategy, and then that time will lead us to the distance. Okay, so again, when I'm showing a problem for somebody that I don't know, I would write this: find time to land. Okay, that just tells the person this is what I'm trying to do, so they're not scratching their head trying to figure out your work. Since this is a uniform acceleration of 9.8 downward, we can use one of those wonderful uniform acceleration equations. So we got them on the reference page, we might as well use them. Notice we're talking about vertical motion here. We have no vertical initial velocity, so we're allowed to call v naught 0. Okay, I sometimes write it y is v naught yt plus 1/2 a sub yt squared. I put these little y's in here to remind me we're just talking vertical. And that's how I know, because I'm not moving vertically at the moment I become a projectile. That's like if you launch something up at an angle or down at an angle. But here it's strictly horizontal. And I'm using 9.8 here. Okay, so my vertical distance is h, and it's 1/2 g t squared. So t is 2h over g square rooted. So that's how long it's going to take to land. And for the horizontal motion, again, just little sketches so that I can tell the grader what to look for. Now we have no acceleration. Remember, in a projectile, there is no horizontal acceleration. All the acceleration happens vertically, and we're done with that. So this is, I guess, the simplest of the kinematics equation, just Vx times t. So we found the t here. The Vx is from part B. And again, I'm going to write this on my test. Okay, so if they're scratching their head, like, where did they get this from? You say it's from part B. Then if you made a mistake in part B, they're not like, well, that's not right. They're going to give you partial credit if you've used a wrong answer from earlier to do correct physics later. Okay, so Let's substitute this in here. So we had radical GL sine theta times radical 2h over g, which, don't worry about cleaning this up too much. I am going to put it all under one big radical. The g's are going to cancel. So I'm going to have 2hl sine theta. Oh, I guess that's it. I don't have a denominator. That looks kind of ugly. So I'm going to rewrite this. Square root of 2hl sine theta is my x. Okay. Think about this too. Does it make sense that if it were a taller table, that it would go further? I hope that makes sense to you. If it were a longer ramp, does it make sense that it would go farther? Well, sure, because it builds up more speed if it's on the ramp longer. If the angle was steeper, does that make sense? Okay, because sine theta, as theta goes up, the sine of theta is going up. So this tells us that a steeper ramp should make for a greater distance. Again, logically, I think that makes sense. Okay, if the hoop is now replaced by a disc, what's going to be different about the distance determined in part C? So there are so many ways to say this. First of all, I want you to recognize it's going to be greater, and then how do you put that into words? Again, you're not going to use equations on this particular AP test. So remember what we were doing up here. We're talking about the speed that got built up at the bottom because this thing had to roll down, and not only does it have to move down, it also has to spin greater. Well, if you're using a disc instead of a hoop, it's easier to spin. The moment of inertia is smaller. That means it's easier to rotate. Easier to rotate means we will build up more speed at the bottom, and therefore we'll launch with a greater speed. Okay, obviously the height's still the same, so we're going to go the same amount of time in the air. Or from an energy perspective, by the time you get to the bottom, all that potential energy has become kinetic energy. But remember, that's a combination of translation and rotation energy sort of coupled together. But if you have a smaller moment of inertia, you have less of your kinetic energy tied up in rotation, which means more of that energy can be in translation, therefore greater speed. Okay, so I would start with this. A smaller I for a disk means it's easier to rotate. So it can build up more speed. Okay. Now you could certainly go back and appeal to the equations and say, well, if I put a 1/2 in here for I, a 1/2 mr squared, which is what a disk is, then this is going to have a 1/2, and I'm going to put a 1/2 here, and you can almost rework the entire problem and see that this comes out, it's like 2/3 g sine theta. That's a greater acceleration instead of 1/2, and then that 2/3 ends up coming down here as well, and you get 2/3 times 2 are 4/3 under the square root, and then you could see it that way. That's a long way to go, and it relies on equations. So all right, well, 25 minutes worth of stuff, but honestly, we covered like 90% of rotation and conservation of energy. I mean, those are like the two most important things you might see. So I really hope you're all watching this because I feel like it can be super helpful. Now, watching it isn't sufficient, obviously. You got to be able to do it yourself. So it's not like, reading a romance novel. You got to kind of tune in and make sure, okay, can I apply this myself? I've given you some practice suggestions for old FRQs. Find some ones that are like this and see if you can apply them. You've got this grading rubrics. See how you do. Don't do them all. I mean, don't do a bunch. Just do the parts you think you might struggle with. You'll have a little more confidence going into the test. Okay. All right. 25 minutes. Way more than I wanted to do, but hopefully it was worth it.